Hello, everybody. Welcome to our Term 2 Head Start lecture for physics. My name is Ishan, and this lecture is part of our autumn lecture series. So, what we're going to be doing for the next two-ish hours is we want to get a head start of all the Term 2 topics. Because the thing is, almost all of the Term 2 topics, mainly fields, is probably brand new. You haven't done much of it in Term 1, and I don't believe you do much of it in year 11. So the thing is, we really want to get a like idea about what you're going to be learning in term 2, because you don't want to go back to school, um, don't want to go back to school, and then and then all this new content is all brand new to you. So we really want to uh, get familiar with all the things that will be asked, and we want to get familiar with all this new topics. For anyone who's watching this online, sorry, online live, feel free to ask any questions in the chat box. Probably me or someone else will be monitoring the chat. So if you have any questions, someone will answer them as soon as possible. Yeah, so this lecture is brought to you by ATAR Notes, and just a little bit about what ATAR Notes does and what ATAR Notes provides is we provide free, a lot of free and paid resources. Some of the resources include lectures, such as these ones. We provide, yeah, so like this lecture, it's like a head start lecture. We also have revision lectures. We also have exam preparation lectures. So that's probably important as you get closer to the exam, say September, October period. I know it feels like a long while away, but trust me, September, October is going to come really quickly. Some other resources that we do provide is a lot of study notes and notes in general. I know for the people who are doing bio and legal, there's lots of flashcards to help you revise for any of the hard stuff or uh, help you with remembering definitions. On top of that, there's a bunch of videos, a bunch of quick study tips, and the final thing that we have that I used personally quite a lot is the ATAR calculator. Because I remember in year 12, every single day I had a new prediction about what my study score would be. And then every day I would put that study score prediction into the calculator to see what that magical number magical number would be. So yeah, so if you are interested in any of these things, head over to the ATAR Notes website. On top of that, we do offer some paid resources, such include group group lecture classes, and we also provide one-on-one tutoring at TootSmart, which is something that I personally do. Right now, for I am tutoring methods, a bit of physics, and a bit of chem. So that's what I've been doing for the past few months or so. Cool. So a little bit about myself before we get started. My name is Ishan, and I graduated last year with a 98. Honestly, physics was actually not one of my favorite subjects. At the start of the year, I really wasn't a fan of physics, but as I started to study it more and started to understand the concepts uh, more deeply, I started to actually enjoy physics, and physics actually became my top subject, and I got a 45 in physics, which scaled up to about 47. And now I am in my first year of university at the University of Melbourne, studying computer science. Cool. So just a quick overview about what we're going to do for the next 2 hours. First of all, we'll start off with some quick revision, some year 11 stuff that you should remember. We'll go over a bit of motion and a bit of circular motion. The reason being is because circular motion is actually quite important in term 2. Uh, if you remember in term 1, you might have done a lot of simple circular motion, say a car going around a roundabout or a roller coaster. We're not doing that in term 2. We're doing a bit some. We're doing a bit of the circular motion that we're going to be doing in term 2 is a bit harder. A bit harder to some extent. We'll be doing circular motion around a planet, circular motion with electrons. So yeah, in some cases, some you could say gets harder. Cool. And the main thing that is in term two is fields. So, fields. So, which is we have three fields in physics that in VCE physics that we care about, which is the magnetic field, electric field, and the magnetic, electric, and gravitational fields. So, what we're going to learn about is how each field interacts with each other and how different fields interact with each other. So, say if you have two electric fields or two gravitational fields, we want to know what happens and the forces that are applied and the direction of the forces and all sorts. From that, we're going to move on to motors, DC motors, and learning about how they work. And from there, we go into Faraday's law and alternators. So that's basically about the production of electricity. So how electricity is produced and like why it's produced. And we'll finish off with some transformers and solar panels, which is something that's been added to the study design. Uh, cool. Because of the new study design change, usually in term two, you would learn about special relativity. You're still going to learn about special relativity, but it's not in term two anymore. They've moved it into unit four, so you'll probably learn about it probably term three, term four ish. Oh yeah, so special relativity, you're still going to be doing it. Uh, yeah, it's just been moved to term three or term four. Cool. So some things that you should remember from year 11 and remember from your term one work is first of all your three Newton laws, and if you've forgotten them, the first one is an object stays in motion unless acted upon by an external force. Your second law is F equals ma, and your third law is every action has an equal and opposite reaction. uh, Newton's laws are not asked very often, but what it does, it helps you explain a lot of your answers better. And if you can, in some way, incorporate a Newton's law, teachers and examiners really like that. So, one example of this is when you're explaining normal force. So, if you can explain it in the way that your normal force that you experience is the reaction force of your weight pushing down on the earth and the earth pushing back on up, pushing back up on you. If you write something like that, teachers quite like that. Go next thing is your constant acceleration formulas, which is all of your motion formulas and pretty much everything that you've learned in projectile motion. It's not this doesn't come back again, but it's good to keep it in the back of your mind because this year is going to fly by, and by the time you get to the end of say term two or term three, you will most likely have forgotten all of the simpler stuff like all your motion formulas, all your Newton laws. So just make sure you're keeping that at the back of your mind and you're going back and revising when you get a chance. Vectors are very important for term two. Pretty much everything that we do here, everything that we do with fields and gravitational, electrical, magnetic, everything that we do involves some type of field. So yeah, very important that you know how your fields, sorry, not fields, your vectors works, and how vector addition works. Uh, cool. Concept of work comes back. What we care about in what we care about this semester or this term is the transformation between kinetic and gravitational potential energy, which is something that you would have done in term one when you were dealing with springs. You might have done those questions where there's a spring and you've compressed a spring and then it's into launched a ball and then you have to calculate the height of the ball. So we do something like that, similar, but instead of launching balls with springs, we are calculating the gravitational potential energy and kinetic energy of satellites orbiting around the Earth. So, a quick tip when you're answering any sort of calculation questions, any question that involves writing down any equations or any calculations, you want to make sure that you actually write the equation down. So in this question, we have a is equal to v squared r. So yeah, make sure that you actually write the equation down. The thing is, you don't get any marks for writing the equation because anyone anyone can write an equation, right? The reason why you want to do this is it helps streamline your thinking process. So when you write the equation, you know first of all what variables you have, what variables you don't have, and what variables you're solving for. So when you write down the equation, you know exactly what variables you're working with, and it helps with substituting, makes substituting easier, and it makes rearranging for the formula a lot easier. Because as you move on, especially when you get to gravitational and electrical fields, the numbers you're going to be using are going to be really, really big or really, really, really small. So you want to make sure that first of all your formula is correct and is rearranged properly before you substitute really big numbers. Because for instance, when you're calculating the force for gravitational fields, you're going to be using big numbers like 6 times 10 to the power of like 24, and you want to make sure that those big numbers are in the right place, because if they're not, you're going to get a completely wrong answer. Yeah, so make sure that you write down your formula. If this was a VCA exam, you this would probably be 2 marks. Your first mark is for correct substitution, which is here, and your final mark would be for your correct answer. Yeah, correct answer with units. The second type of answers that you have to write are like worded theory questions. And the good thing about physics is not English, right? So you don't have to write long, extended essays to any sort of question. If you write dot points are perfectly fine. In fact, teachers actually prefer dot points. There's many reasons for this actually. Dot points is very like easy to mark because you can see here what the student's done. You have 1 dot point, 2 dot point, 3 dot points. So that's point one, point two, point three. So it helps structure your thinking to not only yourself, but it helps structure your answer for the teacher who's marking. So they know, for example, if you read this answer, it's actually a pretty good answer to this question. Explain why EMF is generated in the while loop, blah blah blah. This question at this point of time is not going to make any sense to you, but by the time that you finish this lecture, hopefully this question actually makes sense and the answer makes sense to you. If you want, you can quickly screenshot this answer because it's a pretty good answer, and when you finish this lecture, you can come back to this answer, and you will better understand what's happening. The reason why I say it's a good answer is because first of all, it's stating Faraday's law. So we have theory. We have the theory and it's explaining the theory. It's included equations. So this equation is not going to make sense now, but it's included the equations and it's explained them, and then it's finished off with a good closing final sentence. So this is a pretty good approach of how you can answer any sort of worded questions. And don't be afraid to not use sentences. Just be aware that you can use dot points. The reason why I would recommend not to use sentences is because when you start using sentences, you often start rambling, and when you start doing that, you start to say words that you start to say sentences or ideas that contradict what you've said before. What happens usually, you may have experienced this yourself, is when you're writing a sentence for your answer. The first What happens is like near the end, you start contradicting yourself and you start canceling out what you've said before. And then if your assessor is marking this, they'll be pretty confused about what's happening. So to avoid any confusion with one yourself and any confusion with the teacher, make sure you write your answers in dot points. Cool. So something that you've done in term one, work. Second. Cool. Yeah. So something you've done last term would be work and calculating the work done. We know that work is equal to force times displacement. Yeah. So force is in newtons, displacement is in meters. You may have come across this graph on the right. I don't know if you have, but this graph is a force versus displacement graph. And what we can do from this graph is we can calculate the work done on an object by calculating the area. Because we know we know work is equal to force times displacement. So if you multiply the x-axis by the y-axis, you get force multiplied multiplied by distance, which is meters, which will give us the work done. Yeah, so just keep this in the back of your mind because this is going to be very important for gravitational fields. Cool. The second thing I want to review is inclined planes. Thing with inclined planes, there is uh, three forces. Uh, sorry, there's two forces that's acting on it. First of all is a gravitational force. Gravitational force is always downwards, always straight down. Your normal force, which is your reaction force, is at an angle, so at 90-degree angle to the triangle. And your third force is friction. Sometimes friction is given, sometimes it's not. But if friction was there, you would draw it in the opposite direction. Because friction is it's not pushing it upwards, but it's slowing down the rate at which the box goes down. So friction, while friction doesn't necessarily push the box up, it slows down how fast the box rolls down. So you can kind of say that friction is pushing it up to some extent, but yeah, that's why frictional force is straight upwards. One important thing is when you're doing inclined planes is to make sure that you're drawing your force arrows from the center of the box. A lot of teachers are very picky. If you were to draw your force arrows at the edge of the box, you may or may not get any marks for this. Yeah, so some teachers very picky. So just to make sure that you're getting all the marks possible, draw your force diagrams from the center of the box. Cool. We'll do a quick review about circular motion. Circular motion is quite literally things going in circles, right? And there's three types of circular motion questions that we come across. First of all, first one is the horizontal circular motion. So that's pretty much anything that's going like a car going around a roundabout. Second type of circular motion is the vertical circular motion. So that's all your roller coasters and your Ferris wheels. And the third type is our banked ankles, which is things like your velodrome, or yeah, pretty much that's pretty velodromes, or however you say it, is pretty much the main example of banked angles that we use. Uh, you probably use these formulas in term one. A is equal to v squared r, and a is equal to 4 pi squared r divided by t squared. And we also know that force is equal to mass times acceleration. And if we know that acceleration is given by one of these formulas, we can multiply everything by m, right? Multiply m, and what that does, right? Because we already know acceleration, and when we multiply by the mass, we'll get the force, because force times mass is equal to acceleration. And you might be wondering what this like S symbol is in front of the force. That's basically that's a Greek symbol called sigma, and what that basically means is the total sum of the forces. So when we substitute m into our circular motion equations, we will get basically the sum of all the forces added together. Just keep in mind that these two formulas are in your formula sheet. However, the bottom two formulas, the one where we have introduced m, is not. So it's a good cheat sheet formula to include. Yeah, it's good cheat sheet formula to include. Two things that you have to keep in mind. This formula will give us the centripetal force, and centripetal force is always towards the center of the circle. and centripetal acceleration is given by the formulas above. And the thing is, since we are traveling around a circle, the velocity, the sorry, uh, yeah, the velocity is always changing because you're going around a circle, right? So your direction is always changing. However, one thing you have to keep in mind is speed is always constant. For the most part, is always constant. You're traveling at the same speed, but because your direction is changing, your velocity is changing, and uh, because your velocity is changing, you're experiencing some sort of acceleration, and because you're experiencing acceleration, you're experiencing some type of force. Yeah, so this is the least complicated type of circular motion. Things get a slightly harder when we get into uh, vertical vertical circular motion. So this is for like, imagine if this was a like a Ferris wheel or something, or Ferris wheel, or like a roller coaster. So some just move myself. Cool. Yeah, so some things you have to keep in mind is that depending on where you are on the circle, depends on how you would do your calculations. So for example, if you're at the bottom of a circle, your net force is upwards, and your normal force would be greater than your weight force, which is why when if you ever go on a roller coaster and you ever go down, you feel heavier than you usually are because your normal force is quite a lot bigger than your normal force. Your your normal force, if you were just standing on the ground. If you're at the top, if you're at the top of the circle, your net force is downwards, and your normal force is smaller than your weight force. Just keep in mind that force of gravity is always downwards, and the centripetal force is always upwards, or not upwards, and towards the center. So yeah, so that's where apparent weight comes in, right? So when you're at the bottom of a roller coaster, you would feel heavier because your normal force, or the force that's acting up on you, is a lot greater than your gravitational force. Whereas if you were at the top of the roller coaster, you don't feel as heavy because your normal force is a lot lower than your gravitational force. Uh, this is where the idea of weightlessness comes in. And so weightlessness is basically where you have no normal force acting up on you. So the best example of this would be if anyone's gone to space, right? So if you were in space, there is no normal force acting up on you. So that's why astronauts would say they're feeling weightless, because there's nothing that's pushing up back on them, unlike if they were back on Earth. Um, cool. And the last type of circular motion we have is our banked angles. Uh, Cool. And for banked angles, we usually use this formula. Tan is equal to velocity squared divided by gr, where your angle is the angle of the track. Cool. And from this, we can find something called design speed, which is the minimum speed required so that there's no frictional force that's required to keep you up. There's one slight difference uh, between banked angles versus an inclined plane. So if I were to draw an inclined plane real quick, cool. The net force of an inclined plane is downwards, right? You can kind of see that because if you put a box on an inclined plane, it's just gonna fall down. However, on a circular track, the net force is directly to the left. It's perpendicular to the ground. Uh, yeah, so keep that in mind because often when you're asked to draw draw force diagrams, you have to differentiate if it's a inclined plane or if it's a circular, if it's a banked angle track. So if it's a banked angle track, your net force is acting perpendicular to the ground. And yeah, so with that, you can kind of connect up the triangle like this. And if this is FG, you can connect up the triangle, and then you can solve for any of the other variables if you have at least two of the values. Cool. We'll do a quick practice question with circular motion. So we have this question. We have Julia with a mass of 60. Cool. We have Julia with a mass of 60. Blah 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 blah. She's going on a Ferris wheel, and the Ferris wheel has a radius of 5, and the period of the Ferris wheel is 30 seconds. Cool. The good thing about this question is all of the units are given to us in SI, which makes our life a lot easier. So what we can do, we can substitute all of these values into this equation. And what is the force? Yeah, so what is the normal force acting on Julia? Okay. The normal force when she's at the top of the Ferris wheel. So when she's at the top of the Ferris wheel, wait. I just had to refer to my notes because I nearly forgot this. If she's at the top of the Ferris wheel, we know that the normal force is less than the gravitational force. Normal force is less than the gravitational force, and we know all of this is equal to our circular motion formula, which is in this case we're using 4 pi squared mass times radius divided by t squared, and then substituting all our values, we get the force of gravity, which is 60 times 9.8 minus the normal force is equal to 4 pi squared multiplied by the mass, which is 60, and multiplied by the radius, which is 5, all divided by the time squared. Just because of time, I'm not going to fully solve it, but this is what you would do to find the normal force. Just remember, like, don't do what I did and completely forget that the normal force is less than the gravitational force when it's at the top. So we get force of gravity minus the normal force is equal to all of that, all of the circular motion equation. Cool. So this brings us to our first new topic, which is fields, right? So what is a field? The definition of a field is weird. Here it's saying a field is something that alters a region of space. The more specific definition is a region of space where something is experiencing a force, or it's experiencing some sort of physical thing. The definition is a bit weird, and we don't really care about it. So you just have to accept basically this really vague definition. It really doesn't help, but it's kind of the best that we have. So what we care about, right? So with fields is that when we have two fields and when they interact with each other, they apply a force on one another. One field by itself doesn't really do anything. And the way you can see this in real life is if you have a magnet, right? So this magnet by itself, it doesn't do anything. If you put a magnet like on your table, it's not going to do anything. But if you bring another magnet close to it, the two magnets will attract one another. And that's the force that's being applied when there's two magnets nearby. But when there's only one magnet, there is almost no force there's no force that's being applied to anything. So for a force to be applied, you require two fields to interact with one another. Cool. And this is where vectors come in. Like I said before, vectors are very important for fields because the entirety of vectors is pretty much just, sorry, the entirety of fields is pretty much just vectors. And so what we care about is we have this magnet, right? We want to know in which direction is the field traveling. So if we were to introduce another magnet, which way would the force be acting? So to represent the vectors and represent the direction of which the field is acting on, we use something called field lines. And this is basically just a bunch of lines coming out of a field with arrows that tells us which way the field is acting, right? And one thing you have to keep in mind is when you're drawing any sort of field lines, the field lines should never touch. Field lines can never touch, or they can never cross with one another. And the second thing you have to keep in mind when drawing field lines is that the longer a field line is, the more stronger it becomes, and the more field lines you have, the stronger the field becomes. So for this magnet, for example, if I were to introduce a bunch of extra lines like this, this magnetic field is a lot stronger. Yeah, just because of space, I've like crossed the field lines, but if you were to do this properly in an exam setting or SAC setting, make sure you're not crossing any field lines. Yeah, so the more field lines you have and the longer they are, the stronger the field is. Cool. And the first type of field that we will be dealing with is the first type of field that we will be dealing with is the gravitational field. And the gravitational field comes about with anything that has mass. So anything from the Earth to this pen has some sort of gravitational field. So some things you have to keep in mind. The properties of gravitational fields is gravitational fields are only attractive, right? So if you think about it, you're on the Earth. If you jump up, you fall back down. You don't get shot out into space. So we consider gravity to only be attractive because there's no way that gravity can repel anything. And because of this, because it only has one pole, I can only have one pole, we consider gravitational fields to be monopole, meaning that has one pole. Mono meaning one, and pole meaning pole. Gravitational fields are monopole. Next thing about gravitational fields is that shape is radial. Basically means it's circular, and all the arrows, all the field lines act inwards. So if you see this diagram on the right, all of these field lines are acting towards the center. So what that's telling us is that if you were standing here, if you were standing there, you would experience a force that's very bad, Stickman. You would experience a force that's towards the center. So you would get pulled towards the center of the Earth. That's like what we expect. And the gravitational field is strongest near the mass. So the closer you are to the center of mass, the more gravitational field you would be experiencing. And with that, there is two new formulas. G is equal to gm on r squared, and Fg is equal to G times big M multiplied by little m divided by r squared. So I'll quickly just go through what these formulas are. So big G, the one with the capital G, that is a gravitational constant, and that is given by 6.67 times 10 to the negative 11. This constant is in your data booklet, so you don't have to write it down on your cheat sheet. It's in these um, in this units, newtons per meter cubed per kilogram to negative 2. Really weird unit, but if you were to rearrange for G, that's the unit you would get. Not important right now, but yeah, just keep that in mind. Big M, the capital M, is the mass of the object being orbited. So if you were to imagine the Earth and a little satellite, the big M, the capital M, would be the mass of the Earth. Why? Because the satellite is orbiting the Earth, and the mass of the object being orbited is Earth, because the Earth is being orbited by the satellite, if that makes sense. And all of that is divided by r squared. And that is all equal to G and little g, the little lowercase g. And lowercase g is the gravitational field strength. Basically, how strong is the gravitational field? This is given in newtons per kilogram. And if you're paying attention, newtons per kilogram is the same thing as meters per second to negative 2, which is the same thing as acceleration. So this whole formula, gm divided by r squared, gives us acceleration. And for the second formula, as force is equal to g multiplied by big M multiplied by little m divided by r squared. And what that gives us, it gives us the force between two gravitational fields. And if you remember back to the previous definition, you can only have a force if there's two fields interacting with one another. So if you imagine this satellite, this has one field, and the Earth has another field. So when these two fields are interacting with each other, they are experiencing a force. Cool. It doesn't matter for the second equation, for this equation, since there's two m's, it doesn't matter which m you pick to be big M or little m. But to keep things consistent, what I like to do is for the capital M, I choose the bigger mass, so the mass of the Earth. And for the top equation, for the most part, pretty much 90% of the time, for the top part, since it's only one m, you would usually pick the bigger mass. So in this question with the Earth and the satellite, you would be picking the Earth. Cool. So this is where the whole idea of circular motion comes back. Because if you imagine that we have, again, the same scenario with the Earth and satellite, the satellite is just orbiting the Earth in a circular motion. And if we were to draw the forces on the satellite, there's actually only two forces, right? Compared to when we were doing circular motion, we had gravitational, we had normal force. When a satellite is orbiting, there's only one force that's acting on the satellite, and that is gravitational force. Gravitational force towards the center of the Earth. And this gravitational force pretty much acts as the centripetal force that's keeping the satellite from shooting into outer space. And because it's only experiencing one force, which is gravitational force, in some extent, you can say that the satellite is in free fall. But because it has constant velocity, it doesn't have constant velocity, it has constant speed and experiencing circular motion, it stays at orbit. It doesn't keep falling down. Cool. And because of this, satellites don't really experience normal force because there's nothing pushing back up. Like I said with the astronaut, if the astronaut was in space, there is no normal force that's acting up on the astronaut. So that's where the whole idea of feeling weightlessness comes from. Yes, keep in mind that there's a difference between apparent weightlessness and true weightlessness. Since the astronaut is feeling weightless, we call that apparent weightless. It's not true weightlessness because he still has mass. It's just that he doesn't feel the weight force. Yeah, so there's a slight discrepancy between those two terms. And so what we can do is we know that force is equal to ma. This should be this should be a typo. It's an a. We know just a second ma. We know force is equal to ma, and we know that the forces acting on the satellite is given by mass times g, where g is the gravitational field strength, which you learned before, which was g is equal to big G divided by times m divided by r squared. So cool. So what we can do, we can equate those two, and we can find out that g, or a little g, is the same thing as, sorry, this will come back later. We know the forces acting on the satellite is mg, right? Because g would be something, some gravitational field strength, and when you multiply that by mass, you'll get the force. So we can equate g and m, and then we get this where g is the same thing as acceleration, which we kind of showed before, because g is given in newtons per kilogram, which is the same thing as acceleration. So we know that gravitational field strength and acceleration is about the same thing. So what we can do, because we know g is equal to gm divided by r squared, which is pretty much the same thing as, which is the same thing as saying acceleration, we can combine these three equations. Because essentially, all those three equations are telling us the same thing. It's telling us the acceleration an object is facing around when it's traveling in circular motion. And then what we can do from that is, if we wanted to find the force, because we know force is equal to mass times acceleration, if we multiply everything by m, we get this second set of equations, which gives us the force acting on an object in circular motion. And that is where this equation would come from, which we learned in the previous slide. That force uh, acting on two bodies of masses is given by g times the two m's divided by r squared. And that just came from this formula up here. And we just multiplied that by the mass of the object that's traveling in circular motion. Cool. So as I said, and in one of the, like at the beginning, we care about the energy transformation between gravitational potential energy and kinetic energy. So if you imagine that you're a satellite orbiting hundreds and hundreds of kilometers in space, there's two types of energies that you have. First of all is the gravitational potential energy, because you're so high up, you have some gravitational potential energy, and you also have kinetic energy because you're traveling at a certain speed. So what we can do is we can change the radius of our orbit. And so what we can do, right? So if you're, say, 100 kilometers in the sky, what we can do is we can transform our kinetic energy in so that we can go higher up. And this is basically energy transformations that we were talking about, going from kinetic to gravitational, and gravitational back to kinetic energy. Because you can go the other way around. Say you're at 200 kilometers 200 kilometers above the surface of the Earth, and you're dropping down to 100. All that gravitational potential energy is being converted into kinetic energy. And this is probably what you've done in year 11 we use this formula where gravitational potential energy is equal to mass multiplied by g multiplied by h, where g is usually g sorry g is usually 9.8. G is your gravitational field strength, and at the surface of the Earth, it's usually 9.8, or more specifically, it's 9.81. But the problem is, at different heights, the higher up you go, the weaker the gravitational field becomes. And so we can't really use this formula, m is equal to, sorry, GPE is equal to m times g times h. So we have to find, so how do we find gravitational potential energy if we can't use this formula? And what we do is we use these graphs, our distance multiplied by force graphs. Cool. So we know that work done in joules is equal to force times displacement. And in this graph, we are given force in newtons on the y-axis, and then distance in the x-axis. Keep in mind that this is distance times 10 to the 7. So it's really big distances. So what the question is asking us is to find the change in energy, or the work done, from as we go from 2 times 10 to the 7 to 5 times 10 to the 7. Cool. And the way you would do this, you would find 2, you would find 5. And you would draw up and you would count the squares. What a lot of students do, and it's a pretty common mistake, is that cool, we're finding the change between 2 times 10 to the 7 and 5 times 10 to the 7. So what they would do, they would find 2 times 10 to the 7, they would draw it up, and then it would find the y value. So this is about 500, this is about 50. And what they would do, they would go 500 minus 50 is equal to 450, and that would be the final answer. But that is not how we find, that's not how we find work. And the way you actually find work is you would find the area under the graph. If you were in university, you would be using calculus and integration to find the area under the graph. But because that's just way beyond the scope of VCE, we do a much simpler method and we just count up the boxes. And so if I were to count up the boxes in between those two ranges, we would get 1, 2, 3, 4, 5, 6, 7. It's about 7-ish boxes, right? And to find the GPE from that, we know we have 7 boxes. We know that each box is worth 100 newtons. Cool. If you look at the bottom left, each box is worth 100 newtons, and 100 newtons in the y-axis, and in the x-axis, it's worth about 1 times 10 to the 7. And if you multiply that all together, you get this number, which is 7 times 10 to the 9 joules. So it requires that much energy if you were a satellite. If you were a satellite and you were at 2 times 10 to the 7 and you wanted to increase your orbit to 5 times 10 to the 7, you would require 7 times 10 to the 9 joules just to go from 2 to 5. There's one catch in these questions that happens quite often. In this case, we're given newtons in the y-axis. However, this is not always the case. Sometimes, if teachers are feeling quite sneaky, they can give you the y-axis in either G or A, which is not good because we want force. Because we know force times displacement is the work done. We want everything in force. And to go from G or A to force, we know that force is equal to mass times acceleration, or F is equal to mg. We would have to multiply, you would do the same thing, do the same calculations, but at the end, you would have to multiply by the mass of whatever whatever we're using. Say we're using 1,000 kilogram satellite, you would have to multiply this whole equation by 1,000 if we were given um, gravitational field strength instead of newtons. So yeah, just keep that in mind because it's a pretty sneaky trick that catches a lot of students off guard. Cool. And the next type of next field that we have is electric fields. Uh, so what we call these sort of things are point charges, and point charges are basically a single point with an electric charge. Usually, it's protons and electrons. Keep in mind that protons are the positive ones and electrons are the negative ones. Unlike the gravitational fields that we learned before, electric fields can be both attractive and repulsive. So because of that, um, yeah, sorry, electric fields can be both positive and negative, and because of that, they can be either attractive or repulsive. And they're still considered a monopole. The reason that electric fields are monopole is because you can't have an electron with both positive and negative. It's either positive or it's negative. Same thing with a proton. You can't have a proton that's positive and negative. It's positive, and you can't have a negative proton. And because a point can only have one charge, it's still considered a monopole. Same thing with gravitational fields. It's radial. It's stronger as you get closer to the charge. Uh, One thing that's different is the way you draw the field lines. For the positive point charges, the field lines are drawn radially outwards. So they are going, you can see they point outwards from the charge, whereas the negative ones point inwards. Cool, just as a quick thought experiment, what would happen if I had a positive proton and a negative proton? And if you were to draw the field lines, how would they look like? Just as a quick thought experiment, while I explain the next concept. The next new formula that you have to learn is this. E is equal to kq divided by r squared, where k is another constant, 8.99 times 10 to the 9. Q is your charge and measured in coulombs, usually the charge of an electron or charge of a proton, and r is your distance. And all of that is equal to E, which is your electric field strength, similar to your gravitational field strength. This formula will tell us how strong the field is, depending at what distance you are. And if you're paying attention, this formula is very similar to the formula that we learned before, which was big G m divided by r squared. It shares a lot of similarities. We have r squared at the bottom, we have a constant at the top, and we have mass for the gravity, and we have um, charge for the electricity. Cool. So when we have two, when you have two oppositely charged point charges, they can what they do when you draw the field lines, they sort of link up. And as I alluded to before, the positive ones they go outwards, and the negative one goes inwards. So if you were to draw that in a field diagram, it would like look something like this. But the positive ones, the positive field lines are going to the negative ones. However, if you were to have two like charges, say negative, negative, positive, positive, they would repel. And the most common example of this is if you have a magnet. If you have two south ends, or if you have two north ends, uh, they will repel each other. Cool. So if we were, again, the definition of a field before, if we have two fields interacting with each other, they will experience a force. And this force is given by the formula F is equal to K times Q divided by R squared, where Q is the charge on the first point charge, and the second Q is the charge on the second point, or the second point charge. It's all divided by r squared. And again, it's very similar to the previous equation, which was force is equal to g multiplied by m divided by r squared. And you can kind of see how these two fields are kind of similar to one another. It's crazy to think about that the same formula that's being used to find the force of really big planets and really big stars across the universe is the same formula that's being used to explain the forces of two electrons or two protons. Yeah, so with this equation, to find the force of uh, two charged particles, you can have two positives and two negatives, or you can have positive negative, or you can have positive positive. The charges don't really matter because in physics we usually care about the magnitude and not we care about more about the magnitude. So if we have negative negative, positive positive, it doesn't really matter. So if we have a negative charge, we usually just get rid of the negative and just use the magnitude as it is. Cool. And the next type of electric field strength electric field we have is this thing called a uh, called sort of like a charge plate, right? So we have two plates at the top and the bottom, and there's an electric field in between the plates. And so what we can do, we can find the electric strength of the electric field in volts per meter, given by this formula. And what we can do, we can substitute that formula to find the force, and substitute that into this, and we can find, sorry, wrong equation. We can find the force. And from that equation, we can find the work done. And you can find the work done because we know work is equal to force times displacement. And from the second equation, we know force is equal to QE. And if you were to rearrange the first formula to find the distance, you would get work is equal to Q times uh, Q times E multiplied by V divided by E. And the E's cancel out, and you get work is equal to QV. The thing about this field that makes it special is that it's considered uniform. And what uniform means is that the electric field, the strength of the electric field is equal. So it doesn't matter if you're here, or if you're here. The strength of the electric field will always be same. And if we compare that back to gravitational fields and electric fields, the strength of those two fields really depends on how close or how far away you are from the point. So, for example, the gravitational field, the further up you go, the weaker the gravitational field becomes. And oh, because of this, gravitational fields and electrical fields, we consider them, gravitational fields and fields around a point charge is considered non-uniform, whereas this field around two charged plates is always considered uniform. So what usually happens in these types of questions is we put an electron or a proton somewhere in the middle, somewhere here. And what happens if we were to put an electron, the electron would go to the positive side because opposites attract, right? So if you put an electron, it's going to go down to the positive side. And using the charge of the electron, we can find the force that's been applied because we know Q is the charge. So if we know the charge of the electron, we can find the force, and from the force, we can find the work done on the electron. Oh, and yeah, cool. So we'll do one quick question. An electron is placed between uh, two electric plates, which are 30 centimeters apart. So whenever I see something that's not in SI units, I want to make my life easy. So what I do, I just cross the whole thing out. Cross the whole thing out and just write it in proper SI units to avoid any sort of confusion. So in this way, you don't accidentally sub 30 centimeters into your equation and get the whole thing wrong. So if what I recommend, if we're ever given something that's not in SI units, just cross out the whole thing and write it properly. Cool. It's 0.3 meters apart and we have a potential difference of 20, what is the force acting on the electron? And it's given us this data. The charge of an electron is 1.6 times 10 to the negative 19. Normally, it will be given as negative 1.6 times 10 to the negative 19. But in physics, we care about magnitude. So we don't include the negative. And even in your data booklet, this number will be given to you as it is. No positives, no negatives. Cool. So if you were to solve this, we know that the voltage acting on the electric plate is 20, and we know that the distance between the two plates is 0.3. And then from that, we can find the electric field strength, which would be 20 divided by 0.3, which is about 66.7. And then from that, we can find the force on the electron, which is force is equal to the charge being 1.6 multiplied by 10 to the negative 19 multiplied by 66.7. Just a quick tip, when you're dealing with big numbers such as these, it's often a good idea to bracket off the whole thing because sometimes the calculator will not work as the way you intend. Sometimes the calculator, will not do the multiplication as you expect it to. So just to make sure that doesn't happen, put the whole thing in brackets, especially when it comes to scientific notation. And all of that will come to about 1.07 times 10 to the negative 17 newtons. And because everything is given in 2 sig figs, just to be safe, I would be rounding this answer to 2 sig figs. So 1.1 times 10 to the negative 17 newtons. Cool. And the last type of field we have is magnetic field. And the difference between magnetic field and all the other fields that we've done is a magnetic field is always dipole. The reason why this is always dipole is because you can't have a magnet with only one field. You can't have a magnet with one field. A magnet will always have at least two fields. Cool. And this is basically how a magnetic field line would look like. So it's coming out from the north side, and it's going back into the south. Cool. Yeah. So magnetic field lines always go from north to south. In the same way that for electric field lines, it's always positive to negative. For magnets, it's always north to south. Cool. So this question was actually a VCA question, and it asked us to draw the field diagram of the interaction between these two magnets. So we know that magnets go from north to south. So we can get the easy ones out of the way. So this and this, because we know it's going from north to south. And this is going from north to south for this magnet. Sorry, other way around. Cool. But there's one more thing that is missing, and that is that the two magnets interacting with one another. So we have these two magnets interacting with one another. And so you have one extra field line that's going like this. The reason being is because that north is going to the south of the other magnet. Yeah, so if you can kind of see that what's happening. Cool. Yeah, so the north end of this top magnet is being attracted to the south end of the other magnet. And if you were to do the vector addition, you can kind of see how that's happening, but that's a bit too much. So you can kind of just wing it, and so you can see that the magnet would go from north to south, any north to any south. Cool. So this brings us to our next set of topics, and it's basically interaction between electric fields and magnetic fields. Yeah, we don't care about the interactions between gravitational and electric because At that scale, the gravitational field has almost no impact. So what we do care about is the interactions between electric fields and magnetic fields. And so when we have a moving charge going through anything, it's going to create a magnetic field. And a moving charge is basically a fancy way of saying current, because current is basically a flow of electrons, and electrons are charged. So when we have a flow of electrons, it's creating a magnetic field around a wire. So yes, for example, if this pen was uh, a wire, a copper wire, and we send some current through it, it's going to create a magnetic field around it. And so what we care about, because fields are vectors, we care about what direction is the field going in. So if we imagine this rod to be some copper wire and we pass current through it, we want to find out which way is the magnetic field going. And to do this, we can use a bunch of high-tech scientific equipment, or we could just use our right hand, more specifically our right hand thumb. And so the way you find the direction of the magnetic field is you point your thumb in the direction of the current. So for example, if we were doing this question, to find the direction of the magnetic field, you would point your thumb, get your thumb out. I want you to do this with me because if I do it myself, it's not going to make much sense. So if you get your thumb, you point it in the direction the current is going, and you pay attention to where your fingers are pointing. So for this example, it might be mirrored on. Cool. It might be mirrored. Okay, cool. That's about right. Cool. So if you point your thumb in the direction of the current, I'm just going to do it this way because it's going to look weird mirrored. But yeah, so if you point your thumb in the direction of the current, and you see where your fingers are pointing, and if you're doing this right now, you can see that your fingers are kind of going anti-clockwise, right? And since they're going anti-clockwise, we know that the magnetic field around the wire is going anti-clockwise. You don't have to understand why. You don't have to understand why it works or how it works. Just need to have faith that your right hand thumb rule will tell you which way the magnetic field is going. Right, it's either called right hand thumb rule, or some people like to call it the right hand grip rule. Cool. So on this diagram, right, we can see the magnetic field, and we can see how it's going around the copper wire. You can see how it's going around the copper wire. The problem is, with all these arrows and all this like arrows going around, it's really hard to see what's happening, right? So if you imagine like a bunch of arrows, and it's all trying to represent a 3D thing, right? So this arrow going around the coil is trying to represent the magnetic field going in and around the page, and like in and around the coil, which is really hard to do on a 2D page. So this is where this convention of noughts and crosses comes in, right? So if you were to imagine a big arrow, you have a pointy end on one side, and you have like the feathers at one side. If you were to imagine the arrow coming towards you, what would you see? You would see like the shiny sharp part. But if the arrow, you would see like a shiny sharp part, so something like this, right? If, however, the arrow was going away from you, you would see the feathers of the arrow, which would look something like a cross. And so we can use this idea to help us represent 3D things. So whenever we have a dot, like this, sorry, whenever we have a dot like this, we know that something is traveling towards us, like an arrow. And if we were to have a X like this, we know that, like, we know it's traveling away from us. Yeah, because like an arrow traveling away from you, you would see the crosses. So if you were to represent a field diagram, like if we were to represent this using noughts and crosses, we know that on the right-hand side, the field lines are going away from us. So on this side of the coil, this side of the wire, the field line, the magnetic field is going away from us. So we can write that as x's. We can write that. We can show that by drawing a bunch of x's if it loads. Cool. And on the left-hand side, since it's coming towards us like an arrow, you would see the pointy. You would see the pointy end, the pointy parts. Cool. If it loads. It's taking a bit. Okay, there we go. Yeah. So on the right-hand side, since the magnetic field is going away from us, we can write that as crosses. And on the left-hand side, because it's coming towards us, we can show that as dots. Cool. So now that we know if we have a coil and it's traveling, if we have a copper wire and we are passing current through it, we know that it creates a magnetic field, right? So what if we put that that wire in another magnetic field like this? We have this wire. It's carrying current, and it's in between a magnet. So what's happening, right? So this wire is creating a magnetic field by itself, and it's it's in another magnetic field. And what do we know when two fields interact with each other? They will create a force, right? So we have one field, which is the magnetic field being created by the current, and we have another magnetic field, which is the magnetic field of the north going to south. So if you were to draw the arrows, it would be something like this. Taking a bit of time to load. Cool. So yeah, since there's two fields interacting with each other, there will be a force. And what do we want to know? Since fields are vectors, we want to know one, which way is the force acting, and second, how much force we have, or the magnitude of the force. And the way we do that is by using another rule called our right-hand slap rule. And our fingers, they will represent the magnetic field. Our thumb is going to represent the current, and our palm is going to represent the force. Well, it's called right-hand slap rule for a reason. So our palm is the force. And what we can do is we can line our palm up, we can line our right hand with the diagram. So in this case, we have current that's going away from us. It's going into the page or like into the screen. So we point our thumb towards the screen. Okay. Our second thing we know is we know that the magnetic field is going from right to left because uh, we know it's going right to left because magnetic fields go from north to south. So our thumb is going into the screen. Our fingers are going from right to left, which represents the magnetic field. And from that, oh, sorry. Okay, so it's going to be a bit hard to do it. So our thumb is going into the page. Our fingers are pointing from right to left. And from that, our palm is pointing upwards. And our palm pointing upwards tells us that the force acting on the wire would be upwards. Yeah, so force acting on the wire would be upwards. And we can use this right-hand rule for pretty much anything. So if this current was going in the other direction, we would point our thumb in the other way. If if the north and south will flip, we would point our fingers in the other direction. And yes, from that we can, as long as you know two things, as long as you know the direction of at least two of the things, you can find the third one. And usually for questions, they want you to find the direction of the force. And after we find the direction of the force, the second thing we want to find is the magnitude, or how much force is being applied by the magnet on the wire. And so this brings us to our next equation, which is F is equal to N multiplied by B multiplied by current multiplied by length. Uh, Force is in newtons, we know that. Current is in amps, length is in meters. That's things we already know. There is two new um, variables in this equation. The first one is n, and n is the number of turns. What that means is basically, from for now, well, we are dealing with a single piece of wire carrying current. But in industrial settings, we need more than one wire. So what happens is, instead of one wire, there might be 5 or 10 or 20 different 10 or 20 wires that are carrying the current. And so that n basically represents how many wires are carrying the current. The second variable that we have is B, which is the magnetic field strength, which tells us how strong or not strong our magnet is, and it's given in the units of Tesla. And to anyone's surprise, Elon Musk did not make this variable. It was actually Nikola Tesla, back in like whenever he was alive. So from that, from those two things, from the formula and from the right-hand slap rule, we can find two things. We can find the direction of the force, and we can find how much force. And so if we were to do this question real quick, we know that there's a 30 centimeters piece of wire. So I'll just scratch that out and write 30 meters. So 0.3 meters. Cool. And it's a magnetic field of 0.2 Tesla, which is our B. And there's a current of 2 amps. And cool. So what we can do, we can find the force by multiplying N. N is not given, but in most cases, N will be 1, because it's just a single wire going through. Unless otherwise stated, N is usually 1. So F is equal to 1 times the magnetic field strength, which is 0.2, multiplied by the current, which is 2, and then multiplied by the length, which is 0.3. It's taking a bit of time to load, which is pretty annoying. But yeah, so you'll multiply those three terms, and then you'll get the force. And if you were to try to find the direction of the force, we would use our right hand. So we know that the current is coming towards us, so our thumb would point towards us. We know that the magnetic field is going from north to south, so it would be from left to right. So you point your fingers to the right, and from that we know that our palm is facing upwards. So the force is upwards at whatever the force is. So if you multiply them all together, yeah, I don't have a calculator. So if you were to multiply all those all together, the force would be that many newtons upwards. Cool. The second application of the right-hand slap rule is when we have a point charge. So when we have a point charge. So what we can do, we can put an electron or a proton in a magnetic field. And what that does, it's going to induce some sort of force. Because again, there's two fields that's interacting. The first field is the magnetic field, and the second field is the electric field, or the point charge. So cool. What's happening is, I don't know if you can see that properly, but that is uh, a proton, and it's traveling to the right. And so we want to find what direction is the force acting. The way we do this is, again, by hand slap rule. We know the magnetic field is going into the page because of the crosses. The magnetic field is going away from us. So our fingers point into the screen. Our thumb, okay, so here's the problem. We don't have any current, right? So normally the thumb is the current, but because we don't have any current, we point it in the direction the proton is traveling. So the proton is traveling to the right-hand side. So we would point our thumb to the right. And all of that together, we can see that our palm is facing upwards, and the force acting on the proton is upwards. If, however, instead of a proton, we had an electron, I guess still taking a while. Okay, so instead if we had an electron, you would do the same thing. You would point your fingers into the page because the magnetic field is going into the screen or into the page. But instead of pointing our thumb to the right, we point our thumb to the left, right? So our thumb is the direction in which the positive charge is traveling. In the previous example, the positive charge is traveling to the right-hand side. So we point our thumb to the right. But for the electrons, you do the same thing. But if the electron, let's assume that the electron is traveling to the right-hand side, we would flip our thumb to the opposite side, so the left. It's a bit weird, but it's something that you just have to accept. And one very important thing, when you put a point charge in a magnetic field like this, what happens is for this, right? If you keep following the trajectory of the proton, you can see that at this point, the force is acting inwards, right? So the electron is going to travel, electrons traveling upwards. And if we were to continue on the trajectory, the electron would, is taking, sorry about that. Cool. So the electron would travel in a circle. And when things travel in a circle, it's not a few issues with it not loading. Oh, so you just have to, okay. The electron is going to travel in a circle. And when things travel in a circle, we can use our circular motion formulas. Cool. So this is our circular motion, right? Sorry. Cool. So if we were to complete this trajectory, the electrons would just be traveling in circles. Just be traveling in circles. I don't know why it's okay. Cool. So hopefully this works. We'll travel something like this, right? And we know that force is equal to QBB, which is a new formula. Q being the charge on the point charge, velocity, V being velocity, and B being the magnetic field strength. And then what we can do is we can equate this formula to the formula mv squared divided by r. And from that, if we rearrange for the radius, we get this formula, where radius is equal to mass times velocity divided by q times b. And so what this will give us, it will give us the radius of the circular motion of the electron just going in circles. Cool. So another type of scenario that we can have is if we have two coils next to each other. Sorry, not two coils, two wires that are traveling, that are next to each other, and they are carrying some sort of charge. And then when that happens, um, when two when you have two wires next to each other carrying charge, they will induce a magnetic field. But we want to know, is the magnetic field attracting the two wires, or is it repelling the two wires? So if we have two copper wires going in the same direction as one another, if we have two copper wires and the current is traveling the same direction as one another, the the two wires will attract one another, and if you imagine these two are like the wires, they will attract one another and come together. If, however, the direction of the current is opposite, so if one's going up and one's going down, um, the those two wires will repel one another. And this is something that wasn't tested very much in VCA, but it came up once in last year's physics exam, and it's probably pretty likely to come back again. So it's a good idea to have this in the back of your mind. Cool. So far, we've been looking at the magnetic field around just a single. Cool. Sorry, just a single wire. But what happens if we make a loop with the wire? Okay, now it's loading. If we make a loop with the wire, so we have this loop of wire here, right? And we want to find, and there's a current that's going through it that's given by the arrows and the I, and we want to find which direction is the magnetic field going. And to find this, we can use our right-hand grip rule, which you used earlier, and we can point it in the direction of the current. So let's take this arrow over here, and we know it's pointing upwards. The electric field, the current is going upwards, and we point our thumb upwards, and we can see that our fingers, if you do this, you see our fingers are going in a clockwise direction, right? So if it's going clockwise, we know that on the inside, so over here, the magnetic field would be going away from us, so we would draw X's. And on the left-hand side, the magnetic field is coming towards us, and so you'd write dots. And if you were to if you were to complete this for the entire circle, you would see that the magnetic field looks something like this, where the magnetic field inside the wire is going away from us, and the magnetic field on the outside of the wire is coming towards us. And so what we can do is we're going to apply this same idea to something called a solenoid. And a solenoid is you can see it down here, is basically just a coil of wire just wrapped around each other. And what we care about which way the current is going, and two, which side is the north and the south. Because when you pass a current through the solenoid, it's going to create a north end and a south end, similar to a bar magnet. And the way you can see, we can see which way is the north and which way is the south, is let's just take that small section of coil where I've highlighted it, and if we take our thumb, cool, we take our thumb and you point it upwards, because that at that point the current is going upwards. We can see that the current is going, sorry, not the current, the magnetic field is going like this. It's going anti-clockwise around that point. So it's coming through the middle, and it's coming through the middle and then looping back around. And so the direction of which the magnetic field is going, the magnetic field is going through the solenoid is the direction which is north. So in this example, our magnetic field is going from this side to this side, and so you know that side is north. I know that's a bit confusing, but there's an uh, easier way to do this. So we can use our again right hand grip rule, and this time what we can do is we can point our fingers in the direction of the current, right? So in this in this in this this is the question. You can see how the hand is gripping, uh, like the fingers are gripping the coil in the direction the current is going. So the current is going like current is going like in upwards in the side that's towards us. So the fingers are coming like this, and then the thumb is pointing to the left hand side. And so the direction of which the thumb is pointing is the direction of the north side, which is probably the easier way uh, to figure out which side is north and which side is south. Another way you can figure out the north end and the south end is to imagine if you're looking. Okay, imagine this is an eye. Imagine you're looking down, looking down the solenoid that side, and from when you're looking down that way, imagine you're over here and you're looking there. From that, from when you're looking this way, you can see that the current is traveling in an anti-clockwise direction. And if it's traveling anti-clockwise, you know that side is the north side. If you were to do the same exercise and look on this side, if you were to look from this side, you can see that the solenoid, or the direction of the current, is going clockwise. And since it's going clockwise, you know that the clockwise is the south, and the anti-clockwise is north. So that's about 3 ways you can figure out the direction of north and south from a solenoid. Cool. So what we can do with all this information is we can make a motor. So if we were to say the current is going this way, we can find the direction of the force. So if we were looking at this line from M to L, if we use our right-hand slap rule, we know that the current is going into the page. So our thumb would point into the screen. Our magnetic field is going from left to right. So our fingers would point to the right-hand side. And from this, we know our palm is pointing downwards. So the force acting on that point is downwards and pointing downwards. If you were to do the same exercise on the other side, or this side JK, cool. If you were to do it on that side, we know that the current is going from K to J, so it's coming towards us. So we point our thumb towards us. We know that the magnetic field is still the same direction. It's going from north to south. So we point our fingers to the right-hand side. And then from this, our palm is pointing upwards. So the force acting on this side is upwards. And if you can kind of see what's happening on the left-hand side, uh, this coil is being pushed upwards. And on the right-hand side, this coil is being pushed downwards. Because of this, what it's going to do, it's going to make the motor spin. And this is basically how the most simple version of how a DC motor works. Cool. Skipped a few. So we had this starting position. It's the same question. Only thing is that the current has been reversed. And we can see that on one side, the force is acting downwards, and on the other side, the force is acting upwards. And because of this, it's going to induce a type of spin, right? So this you can imagine the left side is being pushed down, and the right side is being pushed upwards. And you can see it kind of spins in an anti-clockwise direction. Yeah, anti-clockwise direction. Cool. And this thing will continue for the next diagram. So what's happened is the coil has been rotated about 45 degrees, And it's still the same scenario, right? So we have BA, where the force is going downwards, and we have DC, where the force is going upwards. And the coil is being rotated even more. And when we get to this position, um, there's a slight problem when we get here, right? Uh, if we were to use your right hand slap rule, we know that the current will take this side BA. We know that the current is going into the page, and we know that the magnetic field is going from left to right. So the force acting on the side BA is straight downwards. The problem is, if you can't tell, the diagram's a bit weird, but the coil is perfectly perpendicular. So the force acting downwards and the force acting straight upwards here, it's not going to make it's not going to make the not going to make the coil spin. It's going to get stuck there. And so to overcome this, what happens is when we get to this point, position 2, the motor will continue spinning. It'll get to here, point 3, and the momentum of the coil will force it to go to position 4. So it will continue to spin. But there's one thing that we have to keep in mind, and it's this thing where the current is reversed. The reason why the current is reversed is if you were to do this exercise, right, and not change the current, right, if you were to keep doing the right hand slap rule to see which way the force is acting, when we get to position 4, what's going to happen is the force on the coil is going to push the coil back the other way, right? So um, the coil is always traveling anti-clockwise, but if we don't change the current at position 4, the the coil will start spinning clockwise. So what will happen is that every time the coil gets in a vertical position, the motor is going to keep changing direction. So one time it will go clockwise, and then it will go anti-clockwise, and then clockwise, and anti-clockwise. And that is not what we want. We want the motor to keep spinning in one direction. And to do this, we have to reverse the current every half rotation. Yeah. So the way we change the current every half rotation is we use something called a split ring commutator. And this is like a little tool down here. You don't really have to know how it works, but all you need to know is that this tool is what allows the current to switch every half rotation. So every time it switches, the direction of the coil spinning will maintain the same. Cool. So this brings us to one of the new study design points, which is torque. And what torque is, if you remember from year 11, is basically turning force. And a motor is pretty much a thing that turns, right? So anything that turns produces torque. And when we have a motor, we want to maximize the amount of torque. And so to do this, we want to maximize the amount of force. And if you remember from the previous equation, where force is equal to N times LB, which gives us the force on a coil, if we want to maximize the torque, we want to maximize how much force is being acted on the coil. And to do this, there's one of four things we can do. We can either increase the number of turns or the number of wires. We can either increase the current, we can increase the length of the wire or the coil, or we can increase the strength of the magnet. And what this does, you can see this, it makes the motor spin faster. And the faster a motor spins, the more torque will be generated. And the more torque you have, the more power you have to do whatever you have to do. Say you're using a motor to power a car. The more torque you have, the more power you have to move a heavier car. And so we can, so the next thing about electricity is this whole idea of flux. And what flux is basically, it's better if you see a demonstration. So over here, we have a loop, or we have a loop of wire, and it's in a magnetic field, right? So, and at this point, the entire area of the coil is perpendicular to the magnetic force. So at this point, we say the flux is maximum. The reason why is because the field lines, the red field lines, um, there is the most amount of field lines that are intersecting the area of the loop of the wire. So at this point, we say it has max flux. On this side, however, on the third diagram, this has zero flux. Oh, you can't see that. This has zero flux. The reason why it has zero flux is the coil is parallel to the magnetic field, and when something is parallel to the magnetic field, no flux is being generated. And the formula for flux is B, which is the magnetic field strength, multiplied by the perpendicular area to the magnet. So over here in the first position, we have maximum area that is perpendicular to the magnet, and over here on the right hand side, we have no area that is perpendicular to the magnetic field. All of it is parallel. And because of that, we say when the coil is parallel to the magnetic field, it has no flux. And this fancy symbol over here is the symbol of flux. I don't know why they chose that symbol. It's pretty scary looking, but all that's telling us is flux is equal to magnetic field strength multiplied by the area of the coil. And then we can use that formula to find the change in flux. So you can see this little triangle at the front, which means delta. So to find that will be your flux final minus your flux initial, which will give us our change in flux. And then from that, if you divide time divided by the time it takes to go from full flux to zero flux, and you multiply that by the number of loops, so the number of wires, you will get the electromotive force, which is a fancy word of saying EMF, which is another fancy word for saying voltage. So what's happening is if we have if we have a coil in a magnet and we spin the coil, we will produce electricity, we'll produce EMF. So this is what we call an alternator. In the previous example, what we were doing in the motor, we had a battery hooked up to the coil, and the battery was spinning the coil. The battery was inducing a current, and the current was causing the coil to spin around the magnet. In this scenario, what we're doing is we have, let's say, a windmill, and it's spinning spinning this coil around a magnet. And what that does, it induces EMF, and then that in turn creates electricity. And then what we can do is we can find how much electricity is being generated. I'll do this quickly. So the coil has the area of 0.8 and has a magnetic field of 1.2. So we can find the magnetic flux. Cool. We can find the magnetic flux, which is 1.2 multiplied by the area, which is 0.8. Cool. That will give us the flux. And we also know that it takes 0.4 seconds to go from horizontal, so this position, to the vertical position. And you can see when the coil is horizontal, there is no flux. The flux is zero because there's no perpendicular area that is hitting the magnetic field. However, when the coil is vertical, there is and you can see there's all of this magnetic field lines that are intersecting the coil. But when the coil was horizontal, since it's parallel to the magnetic field, there's no flux. And so we can say that the change of flux is 1.2 times 0.8, which is 0.96. We can say 0.96 minus 0, which is still 0.96, because we're going from zero flux to maximum flux. And the change of time would be 0.4 seconds because it takes 0.4 seconds to go from horizontal to vertical. And then it doesn't tell us how many how many turns or how many wires are being used. So if it doesn't tell us, we assume it's 1. So the EMF would be equal to 1 multiplied by 0.96 divided by time. Cool. So when you spin a coil around a magnetic field, you will get this output, which is kind of like a sine wave. If, however, we use the split ring commutator, which we used in the DC motors, you would get this output using a split ring commutator. So what that does, it's because a split ring commutator reverses the direction of the current. All of the negative EMF has been transformed into positive, right? So yeah, so if we were to include a split ring, all the negative becomes positive. However, if we don't include anything, we just include a slip ring, the direction of the current doesn't change. So the EMF produced will look like a sine graph, and you will have positive, negative, positive, negative, positive, negative. The thing is, if you were to hook up a light bulb to something like this graph, it wouldn't really work well because it keeps jumping from positive to negative, positive to negative. And to overcome this, we want to find the average of the sine graph. And to find the average, or find the average of the graph, we use this formula where velocity of RMS is equal to the velocity, not velocity, the voltage RMS, which is basically the usable voltage, is equal to the voltage peak divided by root of 2. And the peak voltage is measured from the y-axis, 0, to the maximum height. So the peak voltage goes from here to here, from here to here. The peak to peak voltage, which is something different, is measured from the bottom all the way to the top. Just make sure you don't get confused between peak to peak and peak voltage, because for any calculations which we want to find the RMS, we always use the peak. So from y is equal to 0 to the maximum. Just keep in mind that this formula, we only use this for AC graphs. And for the DC graph, which was this one, we don't have to use the formula because it's a lot easier to use. And for the AC graph, because of the positive, negatives, we have to use the formula to average it out. And if we were to do a quick question, if you wanted to find the RMS of this graph, we know that okay, so it says the peak to peak is 10. So from the top to bottom would be 5. That means the peak voltage from the y is equal to 0 to the top would be 5. And if you want to find the RMS, the RMS, which is the usable voltage, it would equal to the peak voltage, which is 5, divided by root 2. So whatever that is basically the usable voltage that we can use from an AC output. Cool. So when a coil spins around a magnet, it induces a magnetic. It induces a voltage or an EMF. But it can. But if you close the loop, it can also induce a current, and the direction of the current is a bit more confusing to find, and it comes from the direction of the current. We have to find that by using something called Lenz's law. Just because of time, I I have to skim over this, but what Lenz's law is saying is that any induced current in a loop will be in the direction so that the flux will create, uh, the flux that it will create will oppose the change in flux that it produces. So so to put it more simply, right? So if we have this scenario where this is a coil and this is a magnet, the magnet is moving away from the coil. So if you can imagine it, the flux is decreasing as the magnet moves from where it is to as it moves away. The flux would decrease because there's less magnetic field that is perpendicular to the coil. Because the flux is moving away, because the magnet is moving away and the flux is decreasing, what the system wants to do, it wants to induce current so that the flux will increase. And I'll just quickly show you. The current will travel anti-clockwise. The reason why it's anti-clockwise is if when the current's traveling anti-clockwise, the the magnetic field that it induces would be something like would be okay would go essentially it would go this way. It would go something like this. If you can kind of see that going behind, it's going behind, and it's coming back through the coil, and this will increase the flux because there's like this will increase the flux. It's a bit confusing to understand, and I highly suggest that you go to your teacher to explain this one because this is probably the most confusing and most misunderstood topics, and I don't have much time to explain this properly in detail. So I highly suggest when you go back to school, when you come back to this topic of Lenz's law, you really find lots of examples to properly explain this. But in essence, what you want to remember is the direction of the current will travel in such a way that that the flux that it generates will oppose the change in flux. So if the flux is increasing, the current induced will want to decrease the flux, and if the flux is decreasing, the current will want to increase the flux. Cool. So we have one more topic left, which is transformers. And before we do that, I'll just quickly recap what we've done because it's quite a lot. So first of all, we've done fields, we magnetic, electric, and gravitational. Uh, Monopole versus dipole fields. Monopole meaning only one pole, dipole meaning two. Know the difference between repulsive and attractive. Gravitational forces are attractive. Electric and magnetic can be both. It's really helpful to make a nice, pretty little table so you can quickly summarize each field. So, gravitational, electrical, magnetical. So, monopole, dipole. Is it uniform? Is it non-uniform? And just a list of formulas for each field. We also learned about the right-hand grip rule, which is used to find the direction of a magnetic field in a coil, and the right-hand slap rule, which is used to find the force on a coil or a piece of wire. And we use that to spin a motor, or we can use that to produce electricity, AC or DC. Cool. Transformers are not big metallic robots trying to save the Earth, unfortunately. Transformers are this, slightly more boring. What you may have seen is when you drive around the country. And what a transformer is the most simplest form, it's this. So what we have is we have a primary coil and the secondary coil. And the primary coil is where the current and the electricity is coming in. So we have all this current and we have all this electricity coming in from the primary coil. And this induces a current which will travel from the primary to the secondary coil. And so what this does is in this scenario, we have what we call a step-up transformer. And the way we know it's step-up is because the primary coil has less, the secondary coil has more has more coils than the primary. So it's going from a lower amount to a higher amount. So we can say a transformer is stepping up. So what is it doing? So what's happening is we have voltage, and we have voltage, current, wherever everything that's coming into this primary coil. And what happens with a step-up transformer is the voltage will increase. Well, let's say it increases by a factor of 10, right? So the voltage will increase by a factor of 10, and the current will decrease by a factor of 10. Why is this happening? So what a transformer does, it changes the voltage, but it keeps the power the same. And because we know power is equal to VI, right? If we increase the voltage by 10, and we want to keep the power the same, to do this, we have to divide the current by 10. Cool. So if we increase the voltage by a factor of 10 and divide it by the current by a factor of 10, the power will remain the same. And for a step-down transformer, it's the same thing, but it works the other way. So the secondary coil has less coils than the primary. So we're going from lots of coils to less coils. So the voltage goes from a higher amount to a lower amount. So why do we actually need transformers? So the way electricity works, right? So when you turn on the lights at your house, the electricity is being produced from place hundreds and hundreds of kilometers away, and it's being sent to you from hundreds and hundreds of kilometers of wires. But there is this one formula which you haven't learned, which is power loss is equal to I squared times R. And power loss is bad, right? So if you imagine this factory that's producing all this electricity, it wants to reduce the amount of power it loses. Otherwise, it's just producing power for nothing, right? And this equation of power loss is given by I squared R. So if you can imagine that if we have current and we have some sort of resistance, the power loss increases by a factor of I squared, which is a lot. And if you want to decrease the amount of power that is lost during transmission, we have to use a transformer. And more specifically, we have to use a step-up transformer. And in this case, what's happening is, right, we have a 12,000 kilovolt source, and using a step-up transformer, it goes up all the way to 4,000, right? So when you when the voltage increases by like a lot, by a certain factor, the current will decrease because it's inversely proportional, because we know P is equal to VI. And since we know P is constant, if we decrease the voltage, the current will decrease, right? So if we increase the voltage and the current decreases, what happens to this formula? Where power loss is equal to I squared times R. So if we decrease the current, the power loss will also decrease. And this is why we actually want to use transformers. So if we want to increase the voltage and use lots of high voltage lines, so the current will decrease. And when the current is less, the amount of power that we lose through transmission will be a lot less. Because if you imagine, if you're transporting electricity for hundreds and hundreds of kilometers, all of those little power losses will add up, and it will add up to a very significant amount. And to reduce this, we want to reduce the current by increasing the voltage. Cool. And if you have solar panels at home, you don't have to use the power from the grid. And the new study design wants us to kind of understand how solar panels work. And so basically, a solar panel is anything that's converting light energy into electrical energy. And the way it works is kind of like magic, to be honest. We have light energy that hits. We have light that hits the solar panels, and the light energy gets absorbed by a special type of semiconducting material, which is usually silicon. And because the energy is absorbed into the metal, um, the energy that is absorbed becomes gets transferred into electrons. And when the energy is in the electrons will start flowing. And when you have a flow of electrons, it will create a current. And this process is called as the photoelectric effect. And if you're interested, you can search this up. But the photoelectric effect is something that you will be learning in term 3 and term 4. So basically, you'll understand why this actually occurs, and yeah, you learn a bunch of stuff about photoelectric effect, why it happens, and um, why it supports um, some theories of light. I won't get into much details because I'll end up confusing you. And the last thing about the new study is the design point for Unit 3, is this thing called an inverter. When you have when you have a solar panel, when you have solar panels at home, it is going to produce AC electricity. But the problem is your house, uh, sorry, other way around. When you solar panels will produce DC electricity, but the problem is your house runs on AC. So we need an inverter to convert a DC electricity to AC. And for the scope of VCE, you don't really have to know how it works. All you need to know is that an inverter is required to turn DC electricity from a solar panel into usable AC electricity that you can use at home. Cool. Some quick tips for year 12, making sure that you do all your past VCA exams, because that is quite similarly to what your exam will be at the end of the year. Making sure you're planning out for any SAC weeks, and making sure you're revising your notes, because again, it's very easy to forget the things that you did in earlier in the year. And also for physics specifically, please make sure that you're using a scientific calculator and not a CAS, because CAS calculators will not be allowed in your exam or your SACs. And you really want to get familiar with how your scientific calculator works, because a lot of people go into the exams and they realize they don't know how to use the calculator properly because they've been using the CAS for so long. So yeah, make sure you're always using a scientific calculator as much as possible. And also make sure that you know what's on your formula sheet, because there's a lot of pretty much the entirety of the physics formulas will be on the formula sheet. So you want to make sure you're not wasting space on writing the formulas again on your formula sheet. Cool. So with all that out of the way, okay, I'm very blue right now. Cool. With all that out of the way, thank you for listening. I know, sorry, we went a bit over time. I had to rush through the last few concepts, but I hope you guys learned something, and hope you have a good understanding about the topics to come. So by the time that you get back into school and you start learning this content back at school, you're already pretty familiar with the content and what you're learning. So thank you for sticking around. And if you have any questions, last minute burning questions, if you're watching live, put them in the chat below. Other than that, thank you for listening, and we hope to see you here once again. Bye.